Okay, years and years and years ago, I took my first physics class ever. I took it in college, and at the time I was a biology major, and there were different physics options available, but one class had a reputation for being the hardest class in the community college at Palomar. And so, because I'm an idiot, I decided to take that class because I thought I was super smart and I could do anything. So I signed up for this class. And the teacher's name was Takashi, and he's one of the worst human beings that's ever existed. And he kind of just went out of his way to make the course hard because he thought physics should be hard, and he was just trying to get rid of anybody who wasn't good enough or something like that. So, in addition to making fun of me constantly for being the only bio major in this calculus-based, really hard physics course, he also set up some different labs where often we were set up with the intent that we would fail. So one example of this was as we were learning about energy, like you guys are doing right now, he gave us a lab with a very simple apparatus. It's pretty similar to what you guys see on the screen right here. There was a hanging pendulum, and we had the ability to F a ball into the pendulum, and the pendulum would go up. It would catch the ball, and it would swing up with the ball. And so, based on that, he told us our job using conservation of energy was to figure out what the velocity of the ball was before the impact happened. This seemed pretty easy. We're going to do it right now, and you'll see kind of how, from a energy perspective, it looks like it's pretty simple. So let's start with that. It starts with we have at moment one. This is my E1 right here. This is my E2 here. It looks like we are starting from energy turning into energy, and we have an initial energy of the kinetic energy of the bullet. Oops, the B word. Sorry about that. That then turns into gravitational potential energy of the B word block system. So from there, we can just plug in our formulas. 1/2 mv squared equals mg delta y. But what I actually want to do here is I need to change my mass term. I need to have that 1/2 mv squared equals mass of the B word plus mass of the block times g delta y. Because afterwards, when they're together, their mass is combined. So from there, I just need to solve for the initial velocity. So I can do v squared equals, and then multiply both sides by 2. That would be 2 times m bull plus m blah times g delta y. Oh, I'm sorry. I'm trying to find the initial height. My mistake, not the velocity. Let's go back real quick. So divide both sides by the mass, divide both sides by g, and I get something that looks like this. Delta y equals mv squared all over m bull plus m block uh, uh, times, oh man, all over delta y no, over g. Sorry. I just realized as I was going through the problem that we were asked to do the opposite problem that I've written from the one I wrote here. We were asked to find the velocity. I asked you guys to find the height based off of the initial velocity. Doesn't really change things, but now we can just plug numbers in. We know the mass of the B word. We know the mass of the block. So we can add those together. We know what G is. We know the initial velocity. And the answer that comes out of here, when I plug it all in, let me double check real fast, make sure that I remember what it was from when I wrote the problem, times 50 squared, all divided by 4, all divided by 10. Yep, it works out that the system goes up 0.25 meters. So we did this calculation. We did the lab involving it. Everything mathematically, we thought we understood just fine. But then the result that we got was way off, like way off. And we scratched our heads and redid the experiment 2 or 3 more times. One of the rules in Takashi's class was that if it took you longer than 1 hour to finish the lab, he would start taking off 1 point every 5 minutes that you were late. it was a 3-hour lab class, but if you weren't done in the first hour, you potentially started getting negative points. So we started getting more and more negative points as we were trying to figure out what we did wrong. And by the time we finished this lab, when we finally turned it in, we still hadn't figured out what the problem was, but we already had negative 20 points from being so late. We then got more negative points because we didn't even get the right answer. And it turned out that even though we'd done our math perfectly, we collected our data perfectly, there is a flaw in this. So mathematically, I hope you guys understand what I did with energy here. Physically, I hope you understand what I did with energy here. But there's a flawed assumption here. And the flawed assumption that we made is that the energy of the B word coming in was equal to the energy of the system at the end. But there was a collision. A collision took place, and during that collision, when the B word hits the block, a lot of sound, heat, light, those kind of things is generated, which means you lose that energy from your system. Now, Mr. Takashi had not taught us any of this stuff. In fact, everybody got a huge number of negative points on that lab. He didn't teach us this until 2 weeks later. And while I have remembered that lesson forever, I'm still clearly upset about the negative points. So, takeaway here, I'm hoping you guys learned from the way that I set up this problem, but I want you guys to remember always that if a collision takes place, you're going to lose energy. In our next unit, when we do momentum, we'll learn how to account for that energy loss. But at this time, you guys need to be really careful to watch for where energy might be lost from your system. And if that does happen, you have to, at the very least, after doing the calculations, throw in a piece at the end that says, well, actually, it wouldn't have gone quite this high because we know we lost some energy from the collision. We just don't know how to calculate that yet. So that's it. Hope this helped you guys out. And it definitely was therapeutic for me.